Sections 18.2 and 18.4 Classical and Quantum Mechanical Rotation in 2 dimensions. This is the classical, one-body, 2-dimensional, rigid rotor. Rigid here means the radius r is a constant. We use r0 to denote a constant radius. Both r and v here are vectors. They are always perpendicular to each other. The angular momentum of this particle is the cross product of r and v. The angular momentum vector is perpendicular to both r and v. The kinetic energy of a rotating particle is also called rotational energy. We can calculate its rotational energy here. We still use half mv squared. And this v is the change of r0 theta with respect to time. r0 times theta is the length of the arc that corresponds to theta. When theta is 2 pi, we have the entire circle. Because r0 does not change with time, we can take it out. M times r0 squared is the moment of inertia. So the final result is 1/2 times the moment of inertia times over here the angular speed squared. So d theta over dt is the angular speed, denoted by omega. Again, the angular momentum of a rotating particle is L. L is R cross product P, or R cross product MV. How do we get the cross product of 2 vectors? We'll have to use a determinant here. The first row, I, j, k, are the unit vectors in the x, y, and z directions. The second row are x, y, and z, the 3 components of R. The third row is px, py, pz, the 3 components of P. We can decompose this 3x3 determinant to 3 2x2 determinants. And then L is expressed as a vector with 3 components. Here, x component, y component, and z component. The kinetic energy can also be written as L squared over 2I. L is the magnitude of the angular momentum. I is the moment of inertia. The derivation is right here. I assumed this R0 is perpendicular to P. For a classical 2-body rigid rotor, the derivation and results are just similar as the 1-body rotor, almost exactly same. This is a 2-body rotation, M1 and M2. They both rotate about the center of mass. This distance is R1, this distance is R2. This R is the sum of R1 and R2. When we have a rigid rotor, this uppercase R is a constant. We use R sub naught, R0, for this constant. And then in this case, the kinetic energy of these 2 masses is 1 over 2I times L squared. I is again the moment of inertia, but in this case, I is mu times R0 squared. Mu is the reduced mass of these 2 masses. 1 over mu is equal to 1 over m1 plus 1 over m2. You can also prove that mu is equal to m1 times m2 over m1 plus m2. When we are talking about 2-dimensional 1-particle rigid rotor, we assume the radius of the rotation is a constant. In quantum mechanics, we can easily write out the Schrodinger equation for the one-particle rigid rotor. We have the kinetic energy in the x direction, kinetic energy in the y direction, potential energy, total energy. So on the left-hand side, you are looking at H psi. H is the Hamiltonian operator. H is the sum of the kinetic and potential energy operators. Now we need to apply the constraint here. We know it's a rigid rotor. Therefore, x squared plus y squared is equal to r naught squared. So x is the square root of r naught squared minus y squared. Y is the square root of r naught squared minus x squared. There's one more condition. Let's look at the free rotation of the particle. That means the particle may rotate freely on the ring with a constant radius r naught. But this particle can never escape from the ring. So we say the potential energy is 0 if r is equal to r naught. The potential energy is infinity if r is different from r naught. So again, over here, this means x squared plus y squared is equal to r naught squared. And then the potential energy is 0. It's a free rotation. Over here, what if x squared plus y squared is different from r naught squared? Then the potential energy is infinity. This condition is to prevent the particle to leave the ring. We confine the particle on the ring. To solve this Schrodinger equation, we will have to convert the xy Cartesian coordinates to the polar coordinates in this manner. We say x is r naught times cosine theta, y is r naught times sine theta. And then we divide this equation by this equation. We get tangent theta is equal to y divided by x. Now we use the chain rule to transform this Schrodinger equation in the xy coordinates to theta. This is very complex. First, we need to convert delta psi over delta x to delta psi over delta theta. This is the steps. First, I'm going to say if you change x, both theta and r will change correspondingly. And then psi changes with theta. Psi changes with r. That's why you have two terms here. But in this problem, we're looking at a rigid rotor. So this part is 0. This r is constant. And then we have only one term left. And then over here, this is complicated as well. We can't evaluate delta theta over delta x directly. So basically, we evaluate delta tangent theta over delta x. And over here, this is delta theta over delta tangent theta. Delta theta over delta tangent theta is simply the reciprocal of delta tangent theta over delta theta. And because there's only one variable here, we can also say it's d tangent theta over d theta on the bottom. So again, you are actually looking at delta theta over delta tangent theta right here. And then this is delta tangent theta over delta x when y is held constant. We need this tangent theta because tangent theta is y over x. Now we can evaluate this part easily. This part is simply negative y over x squared. How do we evaluate this? Well, this part is trivial. If you took single variable calculus, you know the result of this is 1 over cosine theta squared. All right, so it's right here. And then we keep doing simplification, reorganization. In the end, we convert delta psi over delta x to delta psi over delta theta. We do the same thing to y. It's over here. And then we need to do the second derivative. The second derivative is simply the first derivative of the first derivative. So I'm applying the first derivative operator to psi, right? And then I'm applying the first derivative operator again, okay, twice. Well, and if you are careful enough, you'll get the same result as this one, All right, this is the result. This is the second derivative of psi with respect to x. All right, you do the same thing to y, so you get this one, and then you put them together, you get this. Fortunately, these two terms cancel exactly. They cancel. How about this term and this term? Well, they can be combined because sine theta squared plus cosine theta squared is just 1. So in the end, we have a very simple expression in the polar coordinates. The Schroding equation for the two-dimensional rigid rotor is simplified to this. Again, this r is a constant. R is equal to r naught. All right. What if r is not a constant? It's going to be much more complicated than this. Now, how do we solve this? It's pretty simple. First, m times r naught squared is the moment of inertia, and then we move this constants to the right-hand side. We get this. We solved similar equations before, but over here, when we solve this kind of equation, here's the trick. We set a new variable m sub l to be the square root of 2ie over h bar squared, and then we have this simple equation to solve. There are two possible solutions. One is a to the power of I times m sub l times theta. The other is e to the power of negative I m sub l times theta. So when you see a plus sign, you can imagine it's clockwise rotation, negative sign counterclockwise rotation. All right, so there can be two different directions. Now you may wonder, why did I use m sub l as the name of this variable, the notation? Why did I choose this notation? It's really bizarre. But remember, in general chemistry, you saw m sub l. You saw m sub l in general chemistry before. It's one of the quantum numbers for the electrons in atom. Remember, n, the principal quantum number, l, the angular momentum quantum number, and then you have m sub l. This m sub l is, in general chemistry, the z component of the angular momentum of the electron regarding its rotation about the nucleus. So just for consistency, we use m sub l here. All right. Okay, these two are two possible solutions. You can rotate clockwise or counterclockwise. The particle can actually rotate in both directions at the same time. And over here, we are looking at this general solution. It may sound weird. How can this particle move in the clockwise direction and counterclockwise direction? Well, this is quantum mechanics. In a particle in the one-dimensional box system, the particle can move to the left and to the right at the same time. Again, this m sub l is a quantum number. Now we'll prove that this quantum number is an integer. This is because psi of theta is equal to psi of theta plus 2 pi. Why is this? Theta plus 2 pi and theta are referring to the same position, right, on the ring. And we learned quantum mechanical postulates. The wave function must be single valued. So at the same position, it's either theta or theta plus 2 pi, it's the same position. The value of the quantum mechanical wave function must be exactly same. So over here, okay, this is the wave function at theta. This is the wave function at theta plus 2 pi. Now, both sides divided by e to the power of I ml theta, we have this equation. We expand this exponential function. We get cosine 2 pi ml plus I times sine 2 pi ml. And then we realize the real part is 1. The imaginary part is 0. So we have cosine 2 pi times m sub l is equal to 1. Sine 2 pi times m sub l is equal to 0. Now let's solve this. The only possible solution is this. M sub l is an integer. Well, you can try any non-integer. You will not be able to satisfy these two equations. Alright, so if m sub l is integer, we know this has to be integer, right? Because we defined m sub l to be the square root of 2ie over h bar squared. Alright? And then we can solve for E, the energy. In this case, the energy of the particle is the rotational energy. Because first, the potential energy is 0, and second, there's only rotation. There's no translation, there's no vibration, it's only rotation. So this E is actually the rotational energy. And this is a two-dimensional rotation. The rotational energy is m sub l squared, h bar squared over 2i. M sub l can be any integer, including 0. Now, why can this m sub l be 0? Remember, in the particle in the one-dimensional box problem, the particle must move. But over here, this rotating particle does not have to rotate. It can have 0 kinetic energy. In that case, its angular momentum is exactly 0. It's possible to measure its angular momentum exactly. The uncertainty is 0. Is this a violation of the uncertainty principle? No, it's not. Now we know its angular momentum exactly. But we have no idea about the angular position of the particle when m sub l is 0. When m sub l is 0, let's look at the wave function. The wave function is here. Okay, the wave function is here. You plug in m sub l equals 0 here, equals 0 here. Psi is a constant. Psi does not depend on theta anymore. And what does that mean? That means this particle is all over the ring. This particle is a wave, and that wave is evenly distributed over the entire ring. It's everywhere on the ring. I have no idea where the particle is. So if you make a measurement of the position of the particle, it can be anywhere on the ring. So actually the uncertainty of the angular position is infinity. Alright, so that's why this is not a violation of the uncertainty principle. We have 0 uncertainty regarding its angular momentum, but we have an infinite uncertainty regarding its angular position. Alright. Oh, by the way, now you can actually calculate the rotational energy of electrons in an atom if you know R naught and if you know m sub l. Alright? By the way, if you have a hydrogen atom with an electron occupying the 1s orbital, this is going to be easy. For the hydrogen atom, if you have the electron in the 1s orbital, L is 0, m sub L has to be 0, and then the rotational energy of that electron is 0. That electron is not rotating at all. Okay, now let's look at a two-particle and two-dimensional rigid rotor. In this case, both particles move. How do we solve the Schroding equation? How do we write out the Schroding equation? It's the same as the one-particle system. You just replace m of one particle with mu, the reduced mass of two particles. This is the equation to calculate mu. 1 over mu is the sum of 1 over m1 and 1 over m2. Also, you can say mu is m1 times m2 over m1 plus m2. The general solution to this Schrodinger equation is here. Well, it's the same as the one-particle system. It's a linear combination of e to the power of plus I m sub L theta and e to the power of negative I m sub L theta. The kinetic energy has the same expression. Again, over here, just pay attention to this I. This I is now mu times R naught squared. Again, m sub L can be 0, but it can be also other integers. All right? In this case, I want to say the angular momentum is exact when m sub L is 0. But the angular position of the two particles. Okay, now we have two particles. It's a two-particle system. The positions of the two rotating particles are completely uncertain. We just don't know where the two particles are.